So I guess while they're dealing with that, are there any questions? Are you guys doing the readings? Yes, so. I know I'm giving you a lot of readings, but it's important for you to do the reading. And especially these two books are very good in explaining the concepts. That's why we chose them. They have different styles. Like this one goes into a little bit more detail. So if you want to know a little bit more about transistors, this goes into the detail of transistors. A little bit, not too much. Whereas the other one doesn't cover exactly the same topics this book covers, but also has a different level of abstraction and very clean and simple way of explaining things. And if you look at the lectures, I usually have a combination of both or my own stuff that's added over here. So I don't necessarily follow a single book in the lectures, and this will become even more clear when we get to the toward the second part of the lectures, or even very soon actually. But you should do the readings because they're immensely beneficial for you. Don't be shy don't shy away from reading books. I know this century is a different century. Like people read only 140 or 280 words or characters in Twitter, right? Books are a bit longer, but you'll learn a lot from these books. And especially the things that I don't cover in the lectures. So these are really a supplement. Okay, it didn't self-destruct yet. Is it going to start? Hopefully. Otherwise, I'll start using the blackboard, I guess. But we will go more slowly that way, which may not be good. We have a lot to cover. But you can ask questions. This is your opportunity. Looks like the system gave you some opportunity to ask some questions. Any questions from yesterday, so far in the course? No? You're just ready to listen to the lecture? That's good. Yes, you have one question. No, I don't. Oh, you don't? Okay, I thought you did. No, you said you were ready. Yes. Oh, okay, I see. Yeah, I'm asking questions too fast, then you can answer. So you're going to deal with this delay when you design your Verilog. So if you're inputting stuff much faster than you can actually read the output, you have a problem, right? Then you'll get garbage because everything will start changing. So you need to hold your input for a while until you read the output correctly, and then feed the new input. Yes?
Actually, I have a question regarding the RAM. What is actually triggering the refresh?
Regarding what?
DRAM. What's actually triggering the refresh? Is it the controller or is it the system that helps the RAM?
Yeah, the question is, maybe you should be using these catch boxes, but is it turned on? I think it is. I don't want to hit anyone, though. That's the downside of these catch boxes. There you go.
Can you hear me?
Yes. Yeah.
So my question was, on DRAM, what is actually causing the refresh? Is it the system or is it the memory controller?
Oh, okay. So what basically triggers the refresh process? Remember, DRAM is supposed to be refreshed. And if you want to know why it's supposed to be refreshed, you can read that book. That book actually has DRAM in chapter 5. Although granted, we are not there at chapter 5 yet, I think. So the thing that triggers refresh is actually the memory controller. It's the memory controller's responsibility to say, okay, memory, refresh yourself at this moment.
Okay.
Now, again, as an architect, if you're thinking of an architect, you can say, oh, why is it the memory controller, right? You could build this into DRAM itself. The DRAM chip itself can automatically refresh itself. Now that has implications, right? If the DRAM automatically refreshes itself once in a while, then somebody else sending requests to DRAM needs to know about it. Right? There needs to be some information because the processor is supposed to be connected to the DRAM. And if the processor the memory controller is in the processor, if the processor doesn't know that the DRAM is refreshing, and if it sends a request, how will you expect to get an answer back? Right? So this is really an interface problem. You have the CPU, you have the memory. I guess we can forget about the slides coming up for a while. And I guess hope that this is being recorded. But you have the CPU, and you have the memory controller here. And you have the DRAM chip. And there's an interface here. And there should be some protocol over here that decides how these two should communicate. This is also called an interface. Oh, something happened. In modern DRAM chips, in modern systems, this is also called a DDR interface. It's not the only memory interface. And DDR stands for double data rate, and there are many versions of it. That's why you get the X over here. Now the question is, you need to have a protocol saying that the memory control... Let's do this thing. I think shutter close, right? And we had something else over here. Light. Was it the speaker? Say it again? Oh yes, it works, but I want to finish this thought over here, since we've started. Do we change the light to speaker? Is that what it was? I don't remember, frankly. It's pretty good, okay. How about this? No? For recording, is this good? Okay, okay, good. So basically, you need to have an interface so that the people who are designing this assume something about DRAM, right? Just like the hardware-software interface, right? Whenever you're programming processors, you need to assume that the processor obeys some interface. Like if you do an add, this is the result you expect. Here again, if you send an address, and let's say you say read from that address, basically you send an address and you send a command. This is part of the interface, for example. And you expect to get the results back at some point. Now the question is, if the DRAM is doing refresh internally, this memory controller doesn't know about that, so when should it send the address? Right? That's one question, right? Maybe, one option could be you send the address and the command and you keep sending them, and the DRAM internally buffers the addresses and the commands, right? And then services them whenever it is ready to service them, and then responds back. So this sort of interface is more an asynchronous interface. We'll talk about synchronous, asynchronous, and sequential logic soon. But basically, there is no synchronization other than the fact that, oh, I send you a request, and then at some point you're going to reply back to me, right? They're operating asynchronously. This is doing its own stuff. This is doing its own stuff. It's sending requests. And at some point, DRAM is receiving them and replying back, right? Okay? So another possible interface could be a synchronous interface. Which is more strict, if you will. Basically, the memory controller and DRAM obeys on a standard saying, if I send an address and a command, let's say a read, I know that this read is going to be responded to by DRAM after some number of nanoseconds. So basically, you agree on a read latency. You agree on a write latency. You agree on a refresh latency. And this is documented so that the person who designs the memory controller now can schedule the requests. It can say, oh, I'm going to issue a read right now, and the result will come back after, I don't know, R nanoseconds, and only after that I can issue another read to that particular memory bank. Does that make sense? Now the memory controller knows everything that's going on in DRAM. So it can actually completely control the DRAM because you've agreed on this interface that basically specifies everything. This is really the master now, right? As opposed to the previous version, now this has to do the refresh, right? This needs to tell DRAM, okay, why don't you refresh? And I know that after, this is actually called TRFC in the DRAM standard today, but let's call it refresh nanoseconds. After refresh nanoseconds, I know that you're going to be done. Now I can send you a read request. Make sense? So that's the beauty of the synchronous interface. Now, DRAM doesn't need to do really anything. It doesn't need to have this buffer because somebody else is controlling it, and it knows how to control it. It orchestrates all of the requests going into DRAM. Asynchronous interface, now you don't need to specify anything maybe, right? That's the beauty of this. In an asynchronous interface, maybe you specify minimal things, although it's harder to make it work. Basically, what you say is, the DRAM, so one specification could be, of course, you need to specify what kind of commands you can send over here. But DRAM may automatically refresh, for example, internal refresh. So the memory controller does not need to deal with the refresh. Why could this be useful? Because whenever you send a refresh command over here, it actually takes power, takes energy. So it could be useful if the DRAM internally refreshes itself so that somebody else doesn't need to tell DRAM to refresh and waste power. It's already a waste of power, refresh itself. And if you're sending the command to refresh, and if you're sending the address, that's even more power. Right? So if you internally refresh, that's good. But now the memory controller doesn't know what's going on in DRAM, so you need to agree on a protocol. So what could the protocol be? Basically, the protocol, one protocol could be this. Basically, the memory controller can send a command anytime, let's say, and the DRAM sends a response back saying, either it says acknowledgement, I acknowledge your command and I'm servicing it, or it says I'm busy, send it again later. That's called a NAC, negative acknowledgement. So this is a very different interface now, right? You don't need to agree on any latencies. You just send commands, basically requests and addresses, of course, with the commands. And then the DRAM sends back an ACK or an ACK. I acknowledge and I'm going to do what you ask for, or please send it again, I'm busy right now. And after the ACK, there's some protocol, of course, for receiving the data back. After some point, the DRAM sends back the response, right? Does that make sense? So these are two different, very fundamental things. Even though I'm talking about these in terms of processor and DRAM, very fundamental because you have asynchronous interfaces or synchronous interfaces on any, whenever you want to communicate between multiple different components. You could do this in software. These could be easily software components communicating with each other. Or it could be software, one could be software, one could be hardware components. It could be different distributed system components. And you always have this trade-off between synchronous and asynchronous. Okay. Make sense? Okay, now let's go into the lecture. How do I do this now? Okay. No, that's the other one. Okay, this is this one. Let's hope that this is working now. So we go back to open, remove the speaker. Okay. Is this good? Yes, or is it too light? Turn off the lights, thank you. Okay, somebody did it for me. Thank you, I appreciate it. Okay, so now you've learned about asynchronous versus synchronous, which you will see again in your designs also. But let's go into the subject of this lecture. I'll go through this relatively quickly since we've already spent some time. So I'm going to give you less of a break, sorry, because we want to cover some topics. But hopefully you'll have a nice weekend after less of a break. That's the trade-off we're going to exploit. Okay, and you know what the required assignment, and if you want to do the optional assignment, please send me an email. And the required readings. As I said, please do the readings. They will enable you to learn a lot more, and you're responsible for it. Although I'm not going to ask you very detailed questions about readings, I expect you to know about them. Okay, so recall we were looking at this, right? CMOS, NOT, NAND, and AND gates. And we've actually covered these three. So hopefully you remember these. This is the inverter, this is the NAND gate, and we put an inverter after the NAND gate, we get the AND gate. So some of you asked, and recall also this, basically this is the general complementary metal oxide semiconductor gate structure. You have the inputs connected to a pull-up network made of PMOS transistors, and PMOS transistors, if you remember, they turn on when the input has low voltage. And you have the pull-down network that's made out of NMOS transistors, and these turn on when the input has high voltage, gate has high voltage. And they're connected to the output this way. And this is the power rail, 3 volts, and this is the ground, 0 volts. And we've discussed this. Basically, you can have series or parallel over here. And when the transistors are in parallel, the network is on, if one of the transistors is on. And if they're in series, all of them have to be on. Okay, so one thing we didn't discuss, and this came up in your questions after the lecture, some of you actually were carefully listening and asked some questions. Basically, PMOS is used this way to connect the PMOS is basically used for pull-up. What does pull-up mean? PMOS transistors are used for pulling up the output to 3 volts, whereas NMOS transistors are used for pulling down the output to 0 volts. And the reason we didn't discuss it yesterday was because I don't want to go to the lower layer of abstraction. And I'm not going to go too much also, but the reason is that these transistors are not perfect switches. They're not equal. So it turns out PMOS transistors pass ones well, but zeros poorly. So they can pass a 3 volt very well, but if you want to pass 0 volts through the transistor, it's not very good. Their mobility is not very good. And the reasons partly are explained in this book, but you won't be satisfied. So you'll have to take a microelectronic design course to understand the real reasons, or read on your own. But this abstraction level explains it well, basically. NMOS transistors, on the other hand, pass zeros well, but ones poorly. The other way around, basically. And as a result, PMOS transistors are good at pulling up the output, and NMOS transistors are good at pulling down the output, and that's why we have this structure. So you could come up with transistors where NMOS transistors are connected to the high up over here, but they won't work very well. You could potentially make them work with a lot of pain. So that's the reason we have the pull-up network over here and pull-down network, pull-up network in PMOS and pull-down network in NMOS. Make sense? If you want the lower level abstraction, take the microelectronics design course. Okay, and also you can see that section over here. Okay, there are other issues that you can dig deeper. I just want to give you a couple of examples as well. What about latency, right? We talked about latency a little bit earlier. So which one is faster, transistors in series or transistors in parallel? Any guesses? If you want to pull down or pull up the output, if you have transistors in series, will that be faster if compared to if you have transistors in parallel? Yes?
Intuitively, I would say in parallel they are faster.
Exactly, yes. Because in parallel, they're not adding up resistance, right? If you're operating them in series, now they're all connected, and the voltage needs to flow through all of the transistors to get connected to the output. Basically, you go through all of the resistance of the transistor. It's very similar to resistors, if you think about it. Basically, series connections are slower than parallel connections, and because you have more resistance on the wire. How do you alleviate this latency? We're not going to talk about it right now, but again, you could potentially go one level deeper and talk about pseudo-NMOS logic, where you try to eliminate the PMOS, but there are other examples of this. Okay, we did talk a little bit about power consumption last time. I wanted to dig a little bit deeper over here also. There are 2 types of power consumption in circuits. One is a dynamic, when you're switching the circuit, meaning when you have an input and that's changing, and the circuit is calculating. And the other is static. Static means when you're not touching anything, you're not changing the input, the circuit is just sitting there. So this happens because of leakage, because circuits are not, again, perfect. Transistors are not perfect, wires are not perfect, and they leak. Okay, let's look at the dynamic one. Dynamic one, the main equation for this, I briefly talked about, is CV square F. Now, what does this mean? Basically, you have some capacitance of the circuit, wires and gates that we have, all have some capacitance. And there's some supply voltage, and there's some charging frequency of the capacitor. How often do you actually charge the capacitor? And dynamic power is calculated this way. Make sense? If it doesn't make sense, you should think about how to derive it. But we don't have time to do it, and this is below the abstraction level of what I wanted to cover. But you should know that we had this discussion yesterday in lecture. Dynamic power consumption is quadratically related to voltage. And actually, in today's systems, in real systems, if you want to increase the frequency of charging, operate the circuits much faster, you need to increase the voltage also. So frequency is correlated linearly with voltage. So if you blink a little bit, you can write this as CV cubed. So essentially, your dynamic power consumption is actually has a cubic relationship with voltage. So if you reduce voltage by 1/2, you will reduce dynamic power consumption by 1/8. So that's one lever of reducing dynamic power consumption in circuits, reducing voltage. If you've heard of dynamic voltage scaling or dynamic frequency scaling, that's all done for reducing power consumption. Okay, there's also static power consumption. Again, these are beautiful things. If you take a microelectronic design course, you will see exactly how things switch and how you arrive at these equations. Static power consumption is basically this. Even though you're not doing anything to the circuit, you're not changing the inputs, things are leaking because you have some amount of short circuit connected from the power supply to the output. So transistors are not perfect again. And this is the static power consumption, basically. You have some voltage, supply voltage, and this is the leakage current. Leakage current is very small usually, but as you reduce the size of the transistors, it turns out this leakage current starts increasing. So it has become a much bigger problem today compared to 20 years ago, or compared to 40 years ago. So this is not negligible anymore. And that's what you get, basically. And if you want to calculate the total power consumption, what you would do is you would sum up the dynamic and static power consumption for all of the components of your circuit. And if you want to calculate energy, hopefully you all know that energy is power times time. So you just multiply it by how long you actually do this for, right? You integrate, basically, the power over time. Okay, there's very, very little more in this chapter. So actually, these books are very good. They cover these concepts. They cover it in very little detail, but if you actually read them, you will get something out of them. Make sense? Okay, perfect. Let's move on now. So this is where we left off, actually. If you remember, we talked about De Morgan's laws, and you should be familiar with it right now. Okay. Yeah, this is a mind. It's not perfect, as you can see, right? There's some leakage going on, or whatever it is. Okay, basically, as I said, De Morgan's laws are conversions between different types of logic functions, and they can prove useful if you do not have every type of gate. And as I said, you could optimize some of your gates really well, right? For example, your NAND gate may be very optimized, or your NOR gate may be very well optimized because of what I described earlier. It could be, the reason could be purely because of the way you have the transistors organized in your gates. So if you have the transistors organized better in some of the gates than the other, you may want to convert everything to NOR, for example, or you may want to convert everything to NAND, right? And if you do that, how do you do that? Well, you do that using De Morgan's laws, right? That's essentially it. And we've already covered this. You should go through the truth tables, but it's very simple. This is one of the laws, and this is the other law, basically. Make sense? And you said that you already know about this, correct? Okay, you have a question.
A lot more space if we replace all transistors by one type of transistor.
Yeah, you said transistor or gate?
No,
the gates, yeah. Yeah, I mean, I just gave an extreme example, of course, right? In modern microprocessors, you have different types of gates. In the extreme, you can actually have all NAND gates, but that may require more space, you're right. So that's the trade-off. But as I said yesterday, NAND is logically complete, NOR is also logically complete, so you should be able to convert any kind of logic equation to all NANDs. But you may not want to do that practically in real life, of course. Okay, so this is where we really stopped, actually, using Boolean equations to represent a logic circuit. And we're going to look at several ways of doing that. We're going to look at standardized forms. And I'll give you the key idea of the sum of products form. This is also called SOP form. Anybody heard of the SOP form? Okay, not many, that's good. So basically, assume that you have the truth table of a Boolean function, and normally you do. The key question is, how do we express the function in terms of the inputs in a standard manner? And the idea is the sum of products form. Basically, you express the truth table as a two-level Boolean expression, that contains all input variable combinations that result in a 1 output. Basically, you go through the truth table, you look at all of those input combinations that result in a 1 output, and write them. Basically, if any of the combinations of input variables that results in a 1 is true, then the output is 1. This is obvious, hopefully. And then you can express the function as OR of all the input variable combinations that result in a 1. I'll give you an example. It's very simple. If your output is 1, you look at the input combinations, and you write them in terms of what we call min terms. And your output will be 1 if any of those input combinations that lead to a 1 is true. Essentially, you have an OR at the end, if any of those input variable combinations, and then you write the min terms for those input combinations, input variable combinations. And I'll tell you what min terms are, but they're essentially the values of the inputs that result in a 1. Okay, so let me give you some definitions because you will see these definitions later on also. So complement, clearly we know what that is, right? It's a variable with a bar over it. Literal is variable or its complement, basically. Yeah. Implicant is a product or AND of literals. These are terms that are used in logic synthesis, but we're going to really look at this part over here. Min term is a product that includes all input variables. So if your truth table has 3 input variables, you need to have all of those variables in the min term. And it's a product form. Basically, it's really the AND of the input variables. So if A is true, B is true, and C is false, this min term is activated. That's 1 line. This basically specifies 1 line in the truth table, right? And if you have 3 input variables, you should have 8 lines in the truth table. Okay. And I'll also define a max term, which is the opposite of this. Basically, it's the sum that includes all input variables. It's really the OR of the input variables. Make sense? Okay, so let's do the min terms, because min term is a little bit more intuitive, I think. People can think about it, think about the ANDs more easily. And it's easier to reason about that. Okay, basically, truth table is really the unique signature of a Boolean function, right? But it's an expensive representation. You don't want to really represent everything as a truth table in the circuit. So a Boolean function can have many alternative Boolean expressions, as we've seen, right, earlier. Earlier, in the last lecture, we've seen that you can reduce the function using some of the rules, transformation rules that we've seen. Distributive laws or identity laws, and we've seen that. But we want a canonical form. Canonical means standard, basically. Standard form for a Boolean expression. This provides a unique algebraic signature for a truth table. And different Boolean expressions, of course, lead to different gate realizations. By starting from a standard form and minimizing it, you can actually have a methodical way of reducing your circuit. That's the key idea over here. You start from a standard form, maybe not very optimized, and then you either feed that standard form into a tool, or you do it yourself, or you use Boolean algebra to simplify that standard form. And that's a very methodical way of starting from the truth table and reducing the equations, if you will, into a small circuit. Ideally, you want small circuits, right? As your colleague over here mentioned. Okay, so let's start with this truth table. This is our truth table that I just made up. We're going to look at the sum of products form. This is also called other things like min-term expansion. You may hear that. Basically, we would like to find all of the input combinations or min-terms for which the output of the function is true. So the output of the function is true over here, right? So we're going to write those cases. 0, 1, 1, 1, 0, 0, 1, 0, 1, 1, 1, 0, 1, 1, 1. So those are the 5 cases. And now we're going to construct the min-terms for it. Basically, the min-term for this is A bar, B, C. A needs to be false, B needs to be true, C needs to be true, then you get a 1. Or this min-term needs to be valued to 1. And it's simple now, right? Basically, all these 5, at least one of these 5 need to be true for this function to yield a true. And I've already said what this is saying. Each row in the truth table has a min-term. A min-term is a product of literals. This is the more formal way of saying that. This is basically the fancy way of saying that 0, 1, 1 corresponds to A bar, B, C, right? Or 0, 0, 0 corresponds to A bar, B bar, C bar. But it's not here because if you have A bar, C, B bar, C bar, your function doesn't evaluate to 1, right? Okay? So each min-term is true for that row, clearly, and only that row. And all Boolean equations can be written in this form. Now, it's a very maximal form, as you can see. This basically gives you all possible input combinations that lead the circuit to a 1. That cause a circuit to evaluate to a 1. Okay. So hopefully it's clear why it works. Basically, this is this input, 1, 0, 1. And this input activates this term. This term becomes a 1 if this input is applied. And only that one will be a 1. Everything else will be a 0, because you're very complete, right? You're really enumerating this truth table in Boolean expression form only for the 1s. So no other product terms will really turn on. So if you have input 1, 0, 1, this is going to be 0, this is going to be 0, this is going to be 0, and this is going to be 0. You can be sure of that. Okay, basically, this is what I said earlier. If inputs A, B, C do not correspond to any product term in expression, you get 0 for output. So if the input is 0, 0, 0, you can go through this. None of the min terms will be activated, so you'll get function equals to 0. Well, it makes sense because you didn't include that in the min term expansion that you were doing, right? You included only these inputs that evaluated to 1s. Okay, makes sense, right? It's simple. But now we have a very standard notation, right? This is our standard notation. You could actually write it for any function that you see. Okay, so we could actually make this even more succinct. Basically, if you agree on the order of the variables in the rows of the truth table, you can enumerate those rows somehow with a decimal number that corresponds to the binary number that creates the input pattern. This is actually much easier explained if you do it this way. Basically, this 1, 0, 0 corresponds to decimal 4, so we're going to rename it as min term number 4 or M4. This is 1, 1, 1 that corresponds to decimal 7. We're going to call it min term number 7 or M7. So your function is really the sum of products of these min terms, M3, M4, M5, M6, M7, right? Basically, you can go back to the previous slide. What is M3? Well, or you can, of course, use a summation notation like this. So M3 is really this one, right? M3 really corresponds to A bar, B, C. Basically, what we've done is we've essentially renamed each of them to M3, M4, M5, M6, M7. But now, if you know the inputs, you know exactly what we're talking about, right? This is really the sum of products of min terms 3 through 7. Make sense? And these are actually beautiful because you could feed this into some synthesis tool, and it can reduce it for you immediately because it knows what you're talking about immediately. Okay? Okay, so we've already talked about this, basically. Basically, this function, ABC, in canonical form or standard form can be written this way. Okay, I'm not going to go through this. This is very simple, but these slides are for your benefit. Now, this is our canonical form, but it's not the minimal form, right? In fact, this is almost like the maximal form. Actually, I'm not going to claim that it's maximal, but it's a maximal form. You could, of course, add more terms to make it more maximal, but it makes almost no sense, right? But we've started with a relatively maximal form that describes this in a standard way. Now you can go and minimize it. You can apply the rules that we've learned, transformation, and you figure out that this actually reduces to A plus BC. Now, if that's not obvious, you should do this exercise on your own. I'm not going to go through it, but I'm going to show you another way of doing it in a much more visual way. So this is one way of doing it. One way of doing this is you go through this Boolean equation and basically figure out, oh, I can combine this, for example. What can you do? Basically, you're combining C. If you realize that A, B bar, C, and A, B bar, C bar, where are they? Okay, there you go. This term and this term can be combined by using the distributive law. And then C plus C bar is clearly a 1, so you can eliminate this. Now you get A, B bar, right? And you could do this for everything over here, and eventually you get this one. And this is the realization. Now, if you'd realize it this way, that would be a much bigger circuit, right? Because you would have 1, 2, 3, 4, 5 3-input AND gates, and 1, 2, 3, 4 OR gates, or 1 4-input OR gate. But now you have something much simpler. So that's the beauty of logic minimization. This is much smaller than what you would get if you literally went and built gates for these. Okay. basically, sum of products formed leads to two-level logic. This is another sum of products formed for some other function, not the one that I showed. This is the logic that you would have, basically, for this function. I didn't put it over for this one because this one is really expensive, right? It'll take a long time to fit into the slide. But this one is also expensive. But it's beautiful because you could actually standardize it, right? You could actually have these connections, all of the inputs, and all possible AND gates, and have a wide OR gates at the end. You could actually standardize the logic that you put the sum of products form also. But again, that'll be expensive. Okay, there's an alternative canonical form which I will talk about very briefly, which is essentially the dual of sum of products. I think this is a little bit harder to understand. That's why I started with sum of products. But basically, product of sums. It's really the De Morgan of sum of products of f prime, or complement. So what does this mean? This means that basically you look at the zero terms as opposed to one terms. You could express this function as this. If any of the max terms belonging to that lead to a zero is zero, you get a zero in the output. Otherwise, you get a one. That's why we have an AND over here. If any of these evaluate to zero, we get a zero. Okay? So these are the sums, these are the products. Each sum term represents one of the zeros of the function, as you can see over here. Does that make sense? So hopefully this is clear. You can go and evaluate it on your own. For example, in this case, this is called a max term. That input activates that term, and for the given input, only the shaded sum term will equal zero. Everything else will be equal to one. And you can convince yourself, because only this one is really activated in that case. And anything ended with zero is zero, clearly, so the output of f will be zero. So you basically figure out which ones are the zeros and AND them. Okay, so this is another way of looking at it. If the input is 0, 1, 0, this is what you get. And then you do the OR, and then you do the AND, and you get a 0. Basically, we're simulating this equation over here right now. Okay, I already said this. So how do you write this product of sums forms? Basically, it looks like this. You find the truth table rows where f is 0. 0 in the input column is a true literal. 1 in the input column is complemented literal. So basically, ABC is this way. So basically, you don't complement it in this case. Remember, this is the dual. So we actually say A or B or C over here, as opposed to A bar, B bar, C bar, which we did in the min term. So this is a max term. Okay? So hopefully it's clear. Any questions? So this leads to a different type of standard form clearly, right? Or you just remember, or you do the other way around, basically. What you do is you figure out the sum of products form, and then you take the De Morgan of that, the De Morgan of the complement of the sum of products form. You get the same thing, product of sums, as opposed to going through this exercise. So you could actually, so these are max terms, so I'm going to put large M's over here. You could also rename these to large M0 through large M7. That's the shorthand notation. And you could express this function as a product of the sums, right? Product of the max terms. Product of max terms 0, 1, 2, 1, 2. And that's what you get, basically. Okay. So clearly, this is not the complement of the function. This is really the real function itself. So hopefully, you should convince yourself of that. Any questions? Okay, now you've learned the sum of product and product of sums forms. Why is it useful? This is a standardized way of expressing a circuit. Expressing any truth table, actually. Truth table is a circuit, essentially, as well. Okay, I'm not going to go through these, but basically, they're useful conversions that are summarized in this slide. I don't want to bore you with all of these. Basically, it says that the sum of products form is equal to product of sums form. But of course, they're exclusive, right? The min terms and max terms you use are exclusive, clearly, because the output is either 0 or 1. And you can do the other conversion, also max term to min term, and you could expand the functions like this. And okay, you can have fun with it, basically. This is what Boolean algebra enables you to do. Okay, so let's move into more advanced things. Let's talk about some combinational building blocks. And as I said, we have a lot to cover. But basically, we would like to have some combinational building blocks that are used to group together into larger building blocks to build more complex systems. What does this enable? This hides the unnecessary gate level details. So if you actually have some block and you could build things out of that block, you could do much better. Now let's take a look at some of these examples. I'll give you some terms over here. So a decoder is basically a circuit. It takes inputs, and exactly one of the inputs is one. Well, this should be outputs actually. Exactly one of the outputs will be 1 as a result, and the rest are all zeros. I'm going to change that to outputs, but that's going to take a while. So you see the latency in the circuit. Well, and I cannot see my mouse. That's an interesting problem to have, isn't it? Okay, I'm going to correct it later. So you need to be able to see your mouse to be able to modify things. I wish I could talk to my computer and fix that. But exactly one of the outputs is 1 and all the rest are zeros. And a decoder basically, it really decodes the inputs. It basically says if A and B, this output is 1, if A and B is 0, 0, this output is 1, if A and B is 0, 1, and dot, dot, dot. So you assert only one single of one of the outputs, depending on the input. So you have n inputs and to the n outputs, and only one is asserted. Basically, you're really detecting the pattern in the inputs, right? You're really detecting what's the pattern of the inputs. You're really decoding what's happening. Well, an example with our person again. Only this gate is activated if the input is 1, 0, as you can see over here. Right. Okay, so why is this useful? Well, this could be an address, and you're decoding that address, right? And you're enabling a word line in memory, in DRAM, for example. And in fact, we'll use this later on to enable a memory location. So if the address is 1, 0, only that one is enabled. Everything is disabled. It's beautiful. You're decoding. Okay, basically interpret a bit pattern, and I've given you these examples. I've already said this, but this could be useful for decoding instructions also, as we will see. So you've fetched an instruction. Sorry, I'm not going to give you a break. We'll end up early, hopefully. But you'll have fun during the weekend, right? Is that okay? I'll give you a very small break later on when we get to the hardware description languages, but it'll be short. So basically, it could be an instruction that you've decoded, and you want to figure out what that instruction is. Is it an add? Is it a load? Is it a multiply? Is it a XOR? Right? And these could be instructions, and you look at the opcode, and the opcode could be 2 bits, and you say, oh, it's an AND. And I'm going to make the circuit do the AND after that. Okay, so that's beautiful, right? Decoder. Have you guys looked at decoders before? Okay, yes, really. Some of you, not everyone. Okay, how about muxes? Again, not everyone. So mux is the opposite, basically. It's really a selector. It selects one of the n inputs that are connected to the output. Basically, you need log 2n bits to control the input. So this is a 2-to-1 mux. So if you look at the circuit, what it does is, if select signal S is equal to 0, it passes A, because it's an OR. If select is equal to 1, it passes B, because this becomes 0, and this becomes whatever B is. Let's take a look at the example. If select is 0, this definitely becomes 0, so it has no effects on this OR gate, and OR gate output is dictated by whatever input comes from A, right? So you're basically selecting between A or B. So this is useful for selecting between stuff. Output depends on the value of select line X. Okay, the animation didn't work out too well here. That's basically how we represent a mux. You have a select line, and select line is usually a control line, and control lines are usually represented with these unshaded triangles, and these are data lines. Data lines are usually represented with shaded triangles at the end. So you select between A and B, and output of C will be dependent on the select signal. Now, this is a 2-to-1 mux. It doesn't take a lot of imagination to figure out how to draw an 8-to-1 mux, 8-input mux. Basically, you have 8 inputs, and you want to select one of them. Well, how many bits do you need in the select line? Anybody? I see 3, yes. Yeah, basically you need a 3-bit select line in that case. And this is your task. This could be a good homework assignment. Again, optional homework. You could draw this in the gate level as a combination of basic AND or NOT gates or NAND gates, or you could do it as a combination of 2 input muxes, actually. Okay, and this is the truth table of the mux, as you can see. Okay, let's take a look at adders. How many of you have seen adders? Full adder? Okay, not everyone, interesting. So binary addition, as you can see, it's similar to decimal addition. You go from right to left, you do one column at a time, and you get one sum and carry bits, right? So these are the carry bits that you get. Initially, you don't have a carry in. So let's take a look at the truth table of binary addition on one column of these. So basically, you get inputs, AI, BI, and carry, and then you generate a carry output and a sum. 1 bit. This is binary, right? So one example is, if all of, one interesting example is basically you add AI, BI, and carry, the output is 1, 0. Basically, you have a carry, and you have a sum that's 0 for that particular digit. Okay, so now let's take a look at that. Basically, you could have n 1-bit additions to construct a binary adder. So you could actually express this 1-bit addition in terms of sum of products form. I'm not going to do that in detail, but this is the sum of products form. Basically, you have 8 of these over here, corresponding to each of these min terms, and you connect the min terms that cause this carry to be all ones into this OR gate, and you connect the min terms that cause this sum to be all ones connected to this other OR gate over here. And there are exactly 4 of those that somehow overlap. So this is your 1-bit adder, essentially. It's called a full adder also, or full adder 1-bit. So now we've abstracted it. This is our gate level. Underneath, now we don't know what it is. It's a module. It has 3 inputs, 2 outputs. Now we can use this module to build a 4-bit adder, to add 4-bit binary numbers. And this is what it looks like. So this is our, I rotated it a little bit to make it fit. But you have 3 inputs, 2 outputs. And this is your adder for digit 0, bit 0. There's no carry in because it's not connected to anywhere. So you feed that to 0. It generates a carry out, which is fed into the next digit. This generates a carry out, which is fed into the next digit, ... and you have the sums over here. So that's a 4-bit adder, basically. So abstraction enabled us to look at the 4-bit adder in terms of 4 1-bit full adders. Does that sound good? Okay, beautiful. Okay. And you can do the addition yourself. I'm not going to do that. So, okay, let's take a look at another building block. It's called a programmable logic array. Basically, a programmable logic array is, again, a 2-level circuit, which is very similar to the sum of products forms. Basically, this is a very common building block for implementing any collection of logic functions one wishes to. It is an array of AND gates followed by an array of OR gates. Well, how many AND gates do you have? Again, it's the number of possible min terms in the sum of products forms. And how many OR gates do you have? It's basically the number of output columns in the truth table. Now, if you have enough of these AND gates and enough of these OR gates, you can implement any function with this programmable logic array. I don't show you the connections over here, but imagine that they're programmable. Basically, any of the output of the AND gates can be directed to any of the input of the OR gates over here. Now, this is programmable logic. Okay, we already said this over here. SOP should make this obvious. Okay, so how do we implement a logic function here? Basically, connect the output of an AND gate to the input of an OR gate if the corresponding min term is in the sum of products form. So essentially, this is a sum of products form, generalized, not generalized, but implemented in a programmable logic. Okay, and I said this already, I think. Basically, you program the connections over here, which are not shown, from the AND gate to the outputs of the OR gate to implement a desired function. Does that make sense? Okay, good. So we've seen other type of programmable logic, FPGAs, earlier in lecture 3, but we didn't. FPGAs have other structures, certainly, and you will see more of the FPGA structures. So this is relatively limited. You can only program the connections from any AND gate to any OR gate over here. It's still powerful. You can implement any logic function, but it's relatively limited. FPGA is a lot more, like lookup tables, ... You could implement a lookup table here also, but you need to think about it. Okay, so let's implement a full adder using a PLA. This is the truth table of a full adder, as we've seen. And this is essentially what the PLA would connect internally. It's essentially the sum of products form, right? And I didn't show you all of the connections to not confuse you, but you will need to do this connection, do these connections. This is your full adder. And if you have an OR gate, if you have a PLA, programmable logic array, that has an extra output, you just don't use it. You don't connect it to anything, right? Make sense? Okay, good. Okay, I think that's, and also this is not connected to any of the outputs because there it's, the output is not a 1 for this min term, basically. No output is a 1 for this min term. Okay, so let me talk about logical completeness, and I'm going to give you a 5-minute break, but then I'm going to breeze through some of the slides, so it's just going to be a 5-minute break. This is really important. I want to talk about it. Basically, any logic function we wish to implement could be implemented with a PLA, right? And PLA, and we've also seen it in the sum of products form, right? Any logic function can be expressed in sum of products forms, which means that this thing that consists of AND gates, OR gates, and inverters is logically complete. You could implement anything with that, and that's true. So that's what this is a definition, basically. The set of gates is logically complete because you can build any circuit to carry out the specification of any truth table you wish without using any other kind of gate. Now, your task is this. NAND is also logically complete, and so is NOR. And you can prove it. You can prove it in different ways. Certainly, Boolean expression is one of them. Okay, so after I finish this, I'll give you a break. Basically, there are more combinational building blocks, and chapter 5 in this book has a lot of them. I would recommend that you start taking a look at them. It'll be very useful. Sections 5.1 and 5.2 talk about the combinational logic blocks. Okay, let's take a break here, and then we'll have more fun with Carnot maps. But the break is, as I said, only 5 minutes. So 14:14. All right. Looks like you had extra 2 minutes. In addition to the break that you had early on. So let's start. So we're going to talk about a very fun concept, logic simplification. I mean, we've been talking about that, but I'm going to give you a very cool way of doing it. Has anybody heard of Carnot maps? Some of you. Do you like them? Yes, I see a very clear yes over there. So that's good. For those of you who didn't know, you will learn about it. Okay, what happened here? Well, basically, this was a full adder in SOP form, right? Sum of products form. And it's beautiful because it has all the min terms in it. You can reason about it. But it's not beautiful because it's a huge thing, right? So our goal is to have the simplified full adder. And this is the simplified Boolean equation. Much better than those min terms. And I didn't draw the picture, but you can draw it. This is a 3-input XOR gate. Sum is just a 3-input XOR of ABC. And carry out is basically a 3-input OR of bitwise combinations of the two variables, each of the two variables. And it's very simple, as you can see. It's much simpler than this, and you can imagine that simplicity. The key question is, how do we simplify Boolean logic? So let's talk about logic simplification. Basically, a Boolean expression that you're given may not be optimal, right? For example, this one that's cooked up. Clearly, this is not optimal, right? You have a lot of terms that look like you can reduce. And you can, yes, and this, if you do the rules, you can reduce it to this. So the goal of logic simplification is you reduce the number of gates and inputs maybe, because some inputs may not even, in this case that's not true, but some inputs may not even appear at the end. And you can reduce implementation cost. And this is really the basis for what the automated design tools are doing today. And a lot of the logic synthesis is done by automated design tools, not always, but a lot of the microprocessors today are designed with this automated synthesis design tools. Okay, so basically there are systematic techniques for simplifications that are amenable to automation. So a key tool is the uniting theorem. Now what does this mean? If your function looks like this, you can unite these things, right? Basically, if you look at this function, it looks like this. B's values change within the rows where f is equal to 1. This is the onset, right? And A's values do not change within the onset rows. So onset is essentially a fancy name for the output where the output is on or true. So A's values do not change, but B's values change. Now what does this mean? An input can change without changing the output. That value is not needed. So in this case, B is really not needed. So B is eliminated and A remains. And you could have thought about that by distributing, using the distributive law earlier. And that's true over here also. A is eliminated and B remains over here. So if you have a function like this, this is what you have, B bar. Because A's values change in the onset, but B's values do not change in the onset. So basically, G is B prime over here. Does that make sense? That's very simple. Okay, so the essence of simplification is really finding two-element subsets of the onset where only one variable changes its value. The single varying variable can be eliminated, right? And that's exactly what we've done over here. And we're going to do this pictorially, if you will. So this is another example. You have a complex case, and you can easily figure out how to apply the uniting theorem that I just talked about, but hard to know if you applied it in all the right places. How do you actually know that you minimize the circuit, right? How do you prove that? Especially in a function that has many, many, many more variables. Even this is not complex, right? This is, you can reason about it and you can maybe prove it. The question is there an easy way for potential simplifications, enabling these simplifications? The answer is yes. Basically, we want to have a geometric or visual representation for Boolean functions, something we can draw and see. And that's the idea of a Karnaugh map. This is called a K-map method also. It's an alternative method of representing the truth table that helps you to visualize adjacencies in up to some number of dimensions. And the dimensions depend on how well you can think geometrically, I think. Some people may think more than 6 dimensions, I don't know. So physical adjacency means logical adjacency in this. So this is a 2-variable Karnaugh map over here, for example. This is a 3-variable Karnaugh map. This is a 4-variable Karnaugh map for these different outputs. Basically, this says if A is 0 and B is 0, the output is 0, 0. Now you can express 2 outputs over here, right? If, for example, if you look over here, look at this one. If A is 1, B is 0, C is 1, the output is 1, 0, 1. Okay? So basically, we did the numbering scheme kind of intelligently over here using what is called a gray code. So if you go from here to here, only 1 bit changes. If you go from here to here, only 1 bit changes. Here to here, only 1 bit changes. Now we're going to use that so that we can group things together and minimize the circuit or minimize the truth table. Okay? I mean, this is obvious, of course. You have only one way of going. Okay, so basically, this is also adjacent. So if you go from here to here, you need to think pictorially a little bit, so you can wrap around. So this thing is actually adjacent to this thing, right? If you look at this, the value of B here is 0, the value of B here is 1, but C stays constant. So if both of these were 1s over here, let's assume that the output is only 1 bit, and you had 1s over here, you could express that 1 as A bar, because the outputs are 1, only if A is 0, and in these 2 cases over here, which means that when C is 1, right? Because B doesn't matter in that case. Okay, I'll give you another example over here. So think about the adjacency also by wrapping around. So it's really a circular thing. Okay, I think I said this. You can wrap around from the columns and from the rows. Okay, so let's take a look at the K-map cover for 4 input variables. So let's assume we have 1 output, 4 inputs, and 4 inputs is input A, B, C, D, and they're laid out in the Karnaugh map using these gray codes. So this is the min-term expression of it, or basically, oh, okay, we're already minimizing it. Okay, let's leave the fun over here. But basically, this is the min-term expression of it. What does this mean? The min-terms that correspond to 0 and all of these are 1s. And hopefully we did this right. So let's check it. Let's pick a random one. Number 13 is, what is that? 13. 1, 1, 0, 1, right? So 1, 1, 0, 0, 1. This should be 1, because that min term is true. Okay, so if you do this if you go through this, you will find that this corresponds to that min-term expansion. Now let's try to minimize it. You could certainly write this using the sum of products form, but that's not our goal. Our goal is to use the Karnaugh map to minimize it. And we're going to do that. Actually, I'm going to do that this way. Is it magic? Basically, what you do is you start looking for ones. Even this is actually not correct. You should really start for the largest number of ones that you can get. And you start circling the largest number of ones. Let's start with this one. This is nicer. So if you look at this, all of these ones are together. Now, what does this mean? This means that CD doesn't matter over here, right? Regardless of whether you have C or D, everything is 1 over here. And B also doesn't matter, because B could be 1 or 0, and we still get a 1. So the output is 1 if A is 1, right? I mean, you could have figured out in some other way also, but this is beautiful, because these are all adjacent to each other. You say, oh, CD doesn't matter, because it's always 1 over here. And B also doesn't matter, and so the output must be 1. Basically, you start by circling the largest number of ones. You get, that is a power of, that is basically 1, 2, 4, 8. You cannot do 6 with this one. And you can think about why not. So, and then you go through the next one. Unfortunately, this is a little bit the other way around. So what is the next number of ones? Now, these could be overlapping. So this is the hard one. These are all adjacent to each other, actually, right? And they correspond to B bar, D bar. Can you see that? Basically, C doesn't matter, right? It wraps around. C is 0, 1 over here. And it doesn't matter what C is, but you're dependent on D. And D's value should be D bar. D's value should be 0. In this case, also, A doesn't matter, because A is 0 and 1 over here. You cover the A. But B's value matters. B has to be 0 for these 4 to be 1. So for all cases where both B and D have to be 0, we get a 1. Make sense? So you need to think visually, of course. And then you go to this 1, 1. So we didn't do this right in this case. You need to start with the big ones. Okay, basically strategy, you circle as the rectangles on K-map as big as possible. That's how you minimize it. You want to group as many ones as possible together. But of course, biggest thing that people forget is the wraparounds. If there was a way of circularly representing it, you will see that those wraparounds, but that's a bit harder to think about. But maybe you can think about a 3D representation also. So that's the idea, basically. So what can be legally combined in the K-map? Rectangular groups of size 2 to the K for any integer K. A cell that has the same value, 1. So you could do this for 1s, you could do this for 0s also, of course. And you will get different functions. All values must be adjacent. Wraparound is okay. So how does a group become a term in an expression? You determine which literals are constant and which vary across the group, just like we did. I mean, these are actually things that I'm just writing down, which we did. You can read it on your own. Basically, you eliminate the varying things and then add the constant literals. So if you have a constant 1, you use x. If you have a constant 0, you use x bar. That's exactly what we did over here, right? The varying things are eliminated. C was eliminated over here because it was varying, 0, 1, so you can get rid of it. But we put D bar over here because D is 0. Okay. So you want biggest groupings, you eliminate more variables in each term. You got fewest groupings, fewer terms altogether. And you OR together all the n terms you create from the individual groups. So let's take a look at one example. We'll look at a 2-bit comparator over here. And this is a fancy comparator. Basically, it takes 2 2-bit values. It checks if they're equal, if one is less than the other, or if one is greater than the other. So how do you actually do this? Basically, you first come up with a truth table. And you can easily come up with a truth table. Hopefully, that's correct. And then you basically draw a K-map for each of the output functions. Because outputs are independent, hopefully. They may not be, but let's look at them separately, because separately is easier. Basically, we have the same K-map. For F1, you're a little bit unlucky. These are the only places you have F1 evaluate to 1. So can you minimize these? There are no adjacent ones here, right? Adjacency is only in the horizontal and vertical directions. It's not in the, that direction basically, diagonal direction. So basically, unfortunately, you're back to the min-term form for F1. And you can easily get the min-term form from here. The function is 1 if A, B, C, D are all zeros, A bar, B bar, C bar, D bar, plus A bar, B, C bar, D, and dot, 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 right? Okay, that's a little bit boring. So let's take a look at this other one. Now we write the truth table on the K-map. This is what we have ones for. And you can ignore the zeros. Basically, I'm not writing the zeros over here. And we start with the biggest possible adjacent ones. That's beautiful. Now let's take a look at what that is. Basically, here you have C, because D is varying over here. So you can also augment it saying, oh, this is C. And here we also have A bar, right? Because B is varying. So the first term is A bar C. And now we're going to do more. So what else do you circle next? Well, you want to eliminate this one. You want to cover that one. But you want to cover it with a maximal number of ones. So you can actually do it this way. You could do only this one, but then you wouldn't eliminate some variable, right? So basically, you get A bar, B bar. These two are 1 only if A is 0, B is 0, and D is a 1. Because now, again, this corresponds to D over here. C is eliminated. Okay, now we want to look at this last one. You want to combine it with the maximum possible ones, and this is the only way you can do it. Maximum possible ones that are a power of 2, right? You cannot combine 3 of them, because, yeah, you have 2 values, right? Okay, and that's B bar CD. Sounds good? And this is the minimal form you get. And F3 is an exercise for you. Hopefully it's really easy after this. Okay, so there are also K-maps with don't care, and these are also nice. Basically, don't care means I don't care what my circuit outputs if this appears as input. Basically, the result is an X. And in this case, you have an engineering choice to use don't care patterns intelligently as 1 or 0 to better simplify the circuit. So for example, if you have a truth table like this, if your input is 0, 1, 1, 0, you don't care what the F is, right? So you can actually pick them to be 0, 0, 0, 1, 1, 0, or 1, 1 to minimize your circuit. Now, when does this happen? Let's take a look at binary coded decimal. Have you worked with binary coded decimal digits? Okay, some of you, not a lot of you. Basically, you encode decimal digits with patterns like this. So this is in binary 0, this is in binary 9. And binary coded decimal means these decimals are coded in terms of their corresponding binary values. Now we're going to add an incrementer. We're going to design an incrementer for binary coded decimal. Basically, when you increment, the decimal sequence looks like this. You increment 9 over here, you add 1, you get a 0 in the output. And this is what your truth table looks like. And your truth table has a lot of X's over here because some of the inputs are not even defined, right? In a binary digit, you cannot have 10, right? As a result, this is really undefined. You should never be inputting stuff like this into the circuit. Does that make sense? Because we're using inputs are only binary digits that corresponds to decimal 0 through 9. So you have a lot of X's over here. For example, here, if you increment, you get this value. Basically, this gives you the truth table of what the incremented value would be. Now you have 4 outputs because you have 4 inputs and you're incrementing them, so you get 4 digits in the end. And this is what the K-maps or Karnaugh maps look like over here. Now let's take a look at the function over here, the Z function, right? So we put a lot of X's over here. So if you don't look at the don't cares, this is what you get. You get A bar, D bar, and you can do it on your own. Again, we covered this part. And in order to get rid of this one, in order to cover this one, you actually combine it with this one over here, wrap around, remember? You get B bar, C bar, D. That's not bad, that's small. But now you can use the don't cares for your benefit. You want to minimize the circuit. Don't cares can be 0 or 1. You don't care. How would you minimize this circuit over here? How would you pick values of 0 or 1 for the X's such that the circuit is minimized? Yes?
Would make all the right column combined with all the left column?
All the left column, yes, exactly. Basically, this is what you would do, right? These you interpret as ones, and now you can combine this and this. You have 8 ones that are adjacent together that form a group, and the result is what? Anybody? So what is this function? Not D, right? And you could easily see that this is D, D covers this, and this part must be not D. You could find out in some other way also, of course, by looking at these values, but if you've drawn this, it's very nice. And not C is clearly, if all of these were ones, you would get a not C, right? And if all of them were ones, what would you get? You would get a 1, right? Your output is always 1. Okay, the summary, Karnaugh maps, it's a formal systematic approach for logic simplification, a visual way, and you can have many variables, and you can have Karnaugh maps with don't cares, as we've seen. Okay, any questions? Yes? I couldn't hear. Oh, so if you're doing it right, yes, you're guaranteed to be minimal. But if you forget some things, you're not guaranteed to be minimal. So you have the human factor in it also, absolutely. Okay, now we have 25 minutes to cover hardware description languages. Now let's go into that, because you need to know this for your labs. But hopefully it'll be fun. Okay, basically we're going to look at hardware description languages, design methodologies, and Verilog. And I'm going to go through these relatively quickly. Hopefully this is obvious. This is a really recent Intel processor. And you'll see what pipeline means, what cores, threads mean, clock means. But this is actually not the highest number of transistors. And we've seen Moore's law last time. So how do you deal with this complexity? You have so many transistors, so many gates. How do you deal with this complexity? And hardware description languages come to the rescue, if you will. Basically, this is how you describe hardware. And this is a fact of life. Whenever you design hardware, you need to use them. This is just like software, right? Actually, you could take Verilog, what we're going to describe, and you could run it in software. That's what simulation is. Okay, you need to be able to specify complex designs, communicate with others in your design group, and to simulate their behavior, so that you know that this is what you really want to build. And you can synthesize. Basically, you can write this language, and somebody automatically synthesizes portions of it, if you write it in a particular way. So you can have an error-free path to implementation, right? If the synthesizer is completely correct and good, then you can write in this language and somebody translates it into gates underneath. So there are many of these hardware description languages. Most popular one is really Verilog. VHDL is also popular, but it's losing popularity, I think. So if you're a VHDL programmer, don't get upset. But if you learn one, the good thing is it's not hard to learn another. And mapping between languages is usually mechanical. This is just like if you know C, it's easy to learn C++, right? Okay, so what are these? There are 2 very well-known description languages, Verilog, and you can read about this. It's not that interesting. But as I said, Verilog is the younger one. So people have actually figured out how to make it better, maybe. So I like Verilog. But I think there's no difference fundamentally between these different languages. In this course, we'll use system Verilog, and if you're in the future, we're actually going to use system Verilog, which is really a branch, something that branched out of Verilog. Okay, so let's take a look at Verilog. Basically, we're going to talk about some design principles, hierarchical design. So how do you deal with this complexity? Well, whenever you have complexity, it's good to have hierarchy. Of course, hierarchy has its downsides also, but when you're designing, it could help. Okay, basically the key question is you look at a component and you break the component into smaller things, and the key question is how many of these do you need, for example. So you can start with some predefined primitive gates and or. You remember that you can actually be logically complete with and or not, or NAND. So you can start with this gate library, for example. And you can build simple modules by instantiating these gates. For example, you can build a MUX on top of these primitive gates, right? And then you can build other modules by instantiating these simple components. So you can have a MUX and a decoder and a memory array to build a memory bank, for example. So basically, this is the hierarchy, as you can see. And hierarchy controls the complexity, similarly to what you have modules or functions in software, right? Functions. If you don't program with functions, then everything becomes a single linear thing, right? That's probably hard to debug. So complexity is very important, clearly. We have so many transistors, and how do you actually do this? I mean, even hierarchical design is not easy, basically. Basically, we would like to describe things in hardware description language and synthesize them to gates. So there are two design methodologies, and normally both are used in design. One is top-down. Basically, you define the top-level module that you would like to use, and identify the sub-modules that you need to make sure that top-level module is implemented well. So you could actually divide this into sub-modules. I call this the divide and conquer approach. You exactly know what you're going to implement, and you figure out what are the sub-modules that you need. And sub-modules have other sub-modules, perhaps, and then you eventually have leaf cells. You come to the leaf cell. So it's like a tree. It may not be a regular tree that looks like this. It may be a branchy tree, but it's like a tree. Basically, leaf cells are circuit components that cannot be divided further. So these could be an AND gate, for example, depending on your abstraction level. An AND gate is not a bad abstraction level for a leaf cell, right? Okay, so bottom up is exactly opposite. You first identify the building blocks that are available to you. Maybe your abstraction level is a mux, right? That's a different design point for a leaf cell than a NAND gate. And you build bigger modules using these building blocks, and you use these modules for higher level modules to get the top level module. So this is two different approaches. Normally you combine both of them in real designs. Okay, let's define a module in Verilog. Basically, a module is the main building block in Verilog. You first need to define a name for it, and our name for this is example. You need to define the directions of its ports, inputs or outputs. In this case, you have 3 inputs, 1 output. You need to name the ports. A, B, C are inputs, Y is output, and then describe the functionality of the module. So now you have a module. This could be well, this cannot be a full adder because you have only 1 output, right? In a full adder, you have 2 outputs, but whatever. This could be this, for example. So this is how you write in Verilog. It's simple, right? This is like a programming language. Has anybody written in Verilog before? Okay, very few. That's good. How about VHDL? Okay, that's even less. So, so I have one data point that reinforces what I knew before. Yeah, Verilog is more common. Actually, if you go to companies, they have their own type of language that's not publicly available. They add their own things, own pragmas, so that they can make the design much easier for their engineers. So Intel's language is very different, for example. I mean, very different in the sense that some names may be very different, but the idea is the same. Okay, so that's a module definition, basically. You do module, name, and module. So you need to obey the syntax, of course, and you can learn the syntax by making some mistakes on your own. So that's the name of the module, port list. Ports have a declared type, inputs or outputs, basically. And we'll look at the circuit description a little bit. Basically, these are identical functionally. So you could list the inputs at the beginning without naming them over here, or you could name them over here. I mean, I personally like this one better. It's much cleaner. But again, this is a style choice. And if you work at a company, they may have a certain style, right? If you do programming, usually good places have styles, and you need to obey the styles, right? Okay, so basically this is not, this is just a syntactic issue. So what if you have multi-bit inputs and outputs? You can also define multi-bit input and outputs. This is called a bus by range. Basically multiple wires that are together. You group them together. So you basically provide the number of bits, range end minus range start plus 1. So one example is this. Basically this is a 32-bit wire, A. This is an 8-bit wire B1, an 8-bit wire B2, right? And this is a single wire signal. Okay, so I would recommend using this. I don't like this in general, and it's weird. Anyway, basically it's good to be consistent. So even if you don't obey a standard way of doing things, as long as you're consistent, it's good. Inconsistency is the worst thing. So if somebody goes and reads your code, they can figure out if you're consistent. If you're consistent, they can figure out what you're doing. But if you're completely inconsistent, you have a problem. Right? Good coding style is always consistent, even if you're doing it wrong. So it's better to be consistent when you're wrong than be inconsistent when you're wrong. So half right is actually worse than always wrong in this case, because somebody else can go crazy trying to figure out your code, right? Okay, manipulating bits. Basically, you can do bit slicing, concatenation. Okay, bit slicing is this, basically. You can have a long bus, and you can have a short bus, and you can assign a short bus to contain bits 5 through 12 of the long bus. Basically, you slice the bits. This has 16 bits, and you get 8 of those for the short bus. And you can do this through this assignment. And you can see the syntax now. It's a wire, it's a wire, it's an assignment, right? You can assign one wire to another as long as they're equal in size. Okay, concatenation, you can concatenate. So y, I mean, we didn't define this, the wire, how many bits is y is, but this is really 4 bits. You're really concatenating 4 bits together. And the 0th bit is A0. A is not here, but you can imagine that it's a set of wires also. This first bit is A0 also. The second bit is A1. The third bit is A2. Okay, basic concatenation. Duplication, if you want one value to, and you would like to fan it out to 4 wires, this is what you do basically. You can do it either way. So basically you have 1 bit, A0, and now you have 4 wires coming out of A0, right? Okay, these are simple hopefully, right? Nothing fancy. And you will see this, when you actually program it, it'll become much more interesting. So this is case sensitive, like many languages. So these are not equal, clearly. And I wouldn't recommend using them in the same program. It's better to, again, be consistent in your naming style and not try to, unless you're trying to obfuscate your program. But if you're trying to obfuscate your program, there are better ways probably. Names cannot start with numbers, blah, blah. These are actually simple things that you can figure out on your own. Okay, so this is important. Basically, there's 2 main styles of hardware description language implementation. And this is true for all hardware description language. One is structural, gate level. This is usually easier to synthesize. This doesn't mean that what I'm going to show you is not easy to synthesize, but usually you can synthesize a structural easily, because it's gate level. You specify the gates, actually. Basically, the module body contains gate level description of the circuit. You describe how the modules are interconnected. You describe how the gates are interconnected inside the module. And each module contains other modules, instances, and interconnections between those. So we basically describe the hierarchy at a gate level. Behavioral, on the other hand, the module body contains functional description of the circuit. So it doesn't need to be gate level. It could be functional. You could say A plus B to add 2 numbers. And that's functional, right? You didn't specify a full adder or some type of adder. But that could still be synthesizable. This could be mapped to a gate level thing by the synthesizer, the translation program that takes your Verilog code and tries to synthesize gates out of it, right? Okay, so this contains logical and mathematical operators, like I said. And the level of abstraction is clearly higher than the gate level in this case, right? So you can have if-else structures, for example. Whereas if you want to do if-else in gates, you'd better use a mux, right? Okay, so many possible gate level realizations of a behavioral description. So if you do gate level over here, you could specify the adder exactly as it is. But if you have A plus B, now the synthesizer has a choice. It could use 10 types of different adders, right? And if you want to know about the different adders, chapter 5 over here. Okay, so practical circuits actually use a combination of both of these things. So let's look at the structural HDL a little bit. So this is a schematic of a structural instantiation of a module. This is the module, and you have 2 submodules, top module and small modules, right? So schematic of module top is built from 2 instances of the small, and they're exactly the same. And let's take a look at the Verilog of it. Basically, this is small. This is a small module, and we've seen this before, something like it at least. And how do you construct the top module? Basically, that's it, okay? You basically specify the inputs and outputs, which is A, select, and C. And you have an output Y, and you have the wire you need to specify. And then you instantiate the small ones, once. And you basically connect the inputs to the appropriate inputs in the module. Basically connect A to A, B to cell, A to A, cell to B, and the output Y to N1, or N1 to Y. And that's how you do it. Basically, you clearly specify over here which input is connected to which wire coming from the top module, and which output is connected to which wire inside this top module. So there's no ambiguity here, right? You clearly say B input corresponds to cell over here. And you instantiate the second one in a similar way. A gets M1, B gets C from the outside, and Y gets Y. So you can have the same names. This may or may not be a good style. Clearly, this is cryptic, right? You want to be in better style. But one thing you could do is this is an alternative. Usually it's not that nice, I think, because now this is basically equivalent to what we just did, A cell and 1. But now you're not saying, for example, this B is connected to cell. You don't say that. Your order implicitly specifies that. You should really obey the order over here. Basically A, B, Y, A cell and 1, and they need to correspond to each other. So you can easily make mistakes if you don't do this explicitly. Okay, so hopefully, but this is a safer choice basically. Any pin order, you can actually reorder them in different ways. Here, for example, A corresponds to M1, B corresponds to C, Y corresponds to Y. You don't need to do it in this order, you could do this in this other order, right? Okay, so these are some good practices. It's better to be explicit than implicit. Again, someone else reading your code can read it better, and also you may read it better in the future, right? You can actually figure out if there's a bug if you explicitly specified what you're connecting. Okay, another example. Basically, Verilog supports some basic logic gates, and these are primitives, and there's a library of those. Basically, these primitives are instantiated like modules, except that they're predefined in Verilog. So you do not need to define a module for them. Basically, and or not, obviously, are some of them. And you don't need a module that says and. But this is essentially a mux. And you can convince yourself that this is a mux. Okay, basically we built a mux out of ands or nots. Let's look at the behavioral part. I think this is hopefully obvious. So structural is very gate level, right? Here we had also gates. Well, we didn't have the description, but you need to have gates over there. Okay, behavioral on the other hand looks like this. This is an example. As you can see, there are no gates here, right? We just use things that you can use in other languages, actually. Verilog is really not that different from other languages, except it's lower level and it's very parallel. So basically, this is your specification. And this is what the circuit looks like. And this is exactly how we implemented that circuit. So if you synthesize this, if you go through this translator, it could give you a circuit that looks like this. Or if it's intelligent, it would minimize the circuit, right? Make sense? We didn't specify and at the gate level, right? We just said that. Okay, what about this? So basically you have bitwise operators in Verilog. You can operate on bits. This is AND, bitwise OR, bitwise XOR, bitwise NAND, bitwise NOR. And you could combine them in many different ways. And this may be much easier to write compared to AND, NAND, NOT, right? ... And again, hopefully this is simple. And this is what it's synthesized to be, potentially. Okay, let's look at more interesting stuff, reduction. So let's assume that you want to have an 8-input AND. If you were doing this at the gate level, you would have multiple ANDs, right? But in Verilog, that's it. That looks like magic, right? Basically, it's the AND of this value, and it's really an 8-input AND. And that's what it looks like. It's just the syntax, right? Syntax is that way. Maybe it's not the best syntax, and it's not the same syntax as some other languages, right? Okay, so as opposed to writing this, you're writing this. And if you were gate level, you would write something else, of course. Okay, so let's look at conditional assignment in behavioral Verilog. This is basically, if you want to have a circuit that does this. If S is true, then Y is equal to D1, otherwise Y equal to D0. We've seen this is a mux, right? This is a selector. Based on the value of the selection input, you select either the D1 or D0 as the output. And it's very easy in Verilog, you use this statement. Has anybody seen this statement before? Okay. If you're programming in C, and many languages have this also. But basically, if S is true, Y is assigned to D1, otherwise Y is assigned to D0. Simple. And now this can be synthesized also, right, to a mux. Okay, this is also called a ternary operator, as it operates on 3 inputs. Well, that's for your information. And this is what it looks like underneath. Right? Okay, cool. Is this fun? Now you've learned the language almost. Now you can speak to these machines. Maybe. Okay, so more complex conditional assignments, you can nest them. Clearly, this is a nested conditional assignment. And this is the more higher level pseudocode of it. Again, it's beautiful, it's simple. And this is another complex conditional assignment. You can think of this as a case statement. If S is equal to 1, 1, do this. Otherwise, if S is equal to 1, 0, do this, blah, blah. Okay, I mean, this is like programming at a higher level language, right? Imagine if you were doing this in the gate level. It's not fun, right? I mean, it could be fun, but it's not productive. Now we've just raised our abstraction level so that we're more productive in programming the hardware. Okay, there's, just like any other language, there's a precedence of operations in Verilog also. For example, not is the highest precedent. Precedence means you apply that operation first, and then you apply the next level operation. Basically, this is a priority order across operations, and the lowest one is a ternary, as you can see in the way we did this today. Okay, I'm in general a programmer who actually likes being explicit. I really don't like code that relies on this precedence order, because I think it's very hard to read. So unless the precedence order is really obvious, for some definition of obvious, it's better not to rely on the precedence order. So for example, I think this is relatively obvious when you do this. You don't want to put parentheses over here, right? When you do parentheses, you clearly specify the order of precedence. But this is obvious, but some of the other ones may not be obvious. Okay, anyway, how do you express numbers? Basically, it's also simple. You first say how many digits, how many bits you have, and the base. It could be binary, hexadecimal, decimal, octal, and the number. And you can also have X or Z values, which we will talk about. And you can use underscores to improve readability, especially if you have a long number. Underscores are interpreted by Verilog nicely. So these are some examples. So if the default is 32 bits. If you don't put 32 over here, if you don't put anything over there, you'll get a 32-bit number, which you may not want. And again, this is bad style. Don't do this. Always give how many bits you have. And you can figure this out on your own. So we talked about floating signals in the last lecture. These are signals that are not connected to anything, basically. It's not driven by any circuit. So I'm going to talk about that a little bit more. You can think of this as a floating wire, an open circuit, also known as high impedance, high Z, tri-stated signals. And this is one example of that in Verilog. Basically, this is called a tri-state buffer. Have you heard of the term tri-state buffer? If you read the book, you will. Basically, a tri-state buffer, if the enabling input is true, the output passes to basically the input. So there's an enabling input and there's a data input. If the enabling input is true, the data input is passed to the output. If the enabling input is false, this circuit doesn't connect the input to the output, and output is left as floating. This is nice when you do not want to load stuff into the output, when you don't want to drive the output, basically, for a given enable signal. Now, why could this be useful? And this is how you do it in Verilog, basically. You assign it this is a 4-bit thing, and you assign 4 Z values. So basically, tri-state buffer enables gating of different signals onto a wire. This is the truth table of it. You have an enabling input, and you have a data input, A. If the enabling input is 0, your output is Z, floating. If your enabling input is 1, your output is A. That's exactly what it is, and this is from your book, as you can see. So when could this be useful? Imagine a wire connecting the CPU and memory, and that wire is shared between the CPU and memory. And you can have, you want, basically at any time, only the CPU or the memory can place a value on the wire, but not both. So you have a shared bus, let's call it a wire or set of wires. Sometimes CPU wants to communicate something to memory, and there should be some other thing over here, but we're going to ignore that. But if CPU wants to load something onto the bus, you enable this and you disable this. When you disable this, memory doesn't drive the shared bus, and shared bus value doesn't get touched. If you want the memory to drive the shared bus, you enable this, you disable this. Now, if you make a mistake and enable both, good luck. You can get a garbage out of that, unless they're both transmitting the same value, right? Okay, So this is the truth table for an AND gate that is expanded to include not just 0 or 1 as potential values, but Z, and also don't cares. Remember the don't cares, we've seen 2 different values, floating and don't care. And you can go through this on your own, but for example, if the one input of an AND is Z, and the other input of an AND is 0, that's fine. Because 0, basically, whatever you AND with 0 is 0, so it doesn't matter what this input is. But if both inputs are Z, you don't know what the value is. Okay. Okay, what happens with HCL code? Well, we'll look at, I'm going through this relatively quickly because we have only 1 minute. But basically, I think I've covered most of what I wanted to cover, so this is good. And I'll leave the rest of the slides so that you can study if you need it for your labs. But basically, you have synthesis tools. Modern tools are able to map this hardware description language code into low-level cell libraries. They can perform many optimizations. However, they cannot guarantee that a solution is optimal, mainly due to expensive computational placement and routing algorithms that you can read about in the paper also. So the most common way of digital design these days is synthesis. But in the labs, you will do a lot of simulation also, because if you do simulation means you basically simulate a circuit. This allows the behavior of the circuit to be verified without actually manufacturing the circuit. This is really important. And you should look at the other slides if you want to look at what simulation looks like. Okay, have a good weekend. I'll see you next week.